This is video number 2 for sections 5.1 and 5.2, inverse functions and tables. So now I'm ready to help you understand the idea of an inverse function. Take a look at this picture here. I've made up a fresh composition of function problem. My first function machine, f of x, is f of x equals x plus 5, a linear function. And my second function, g of x, is also a linear function. G of x equals x minus 5. Well, let's pick a number and stick it into the in slot of the f function. How about 3? And then let's figure out what comes out. It's very simple. If I stick 3 in here, I just replace all the x's with 3. 3 plus 5, of course, is 8. And then remember composition. Now I take the 8 and I stick it into the next function. And let's see, what would come out? G of 8 would be 8 minus 5, which is 3. Well, that's kind of interesting. I started with a 3, and I ended with the same number. Let's run through that again. Let's try a new number. How about 7? You can try something else if you want to. If I stick it in here, 7 plus 5 is 12. And then if I take the 12 and stick it into the second guy, 12 minus 5 is 7. The same thing happened. I keep ending up with the same number I started with. Well, take a look at this definition here. When one function reverses the process of the original function, which is essentially what happened, the second guy keeps undoing what the first guy did. When one function reverses the process of the original, we call it an inverse function. And we actually have a special way to write down the equation. Instead of using g of x, instead of thinking of that second function as a brand new function, we write f inverse of x equals x minus 5. This is the notation for an inverse function. It's kind of annoying, I know, because you see that -1 there, and it makes you think of exponents. This has nothing to do with exponents. It has nothing to do with reciprocating bases or anything like that. It's just a notation. It's just to save me from writing inverse, inverse. It's just shorthand. So even back here in the function machine, I would be calling this f inverse x equals x minus 5. Hopefully you can see with this simple example we did that it's kind of obvious why this worked out this way. I mean, after all, the first function, all it does is add 5 to whatever you give it. Well, if then you go and you subtract 5, of course, you're just going to be back where you started. So it's not a complicated idea. We're just saying the second function essentially undoes or reverses whatever the first function did. There's a second way that you can view what's going on with an inverse function. When you compare an inverse function to the regular function, what you notice is that all the inputs and outputs have switched places. You can even see that in our example up here. In the original function, 7 went in and 12 came out. Whereas in the inverse function, 12 is going in and 7 is going out. The inputs and outputs have swapped places. We had earlier the 3 going in and 8 coming out for the original, and 8 went in and 3 came out for the inverse. Both of these definitions, I think, are helpful in terms of keeping in mind what an inverse function actually is and does. Okay, so with that as a little bit of background, let's go ahead and try an example. And in this video, we're just going to concentrate on using tables. Here is a table of a function. I called this function f of x. I've got, of course, the x column and the output column, the y column. Let's see if we can find each of these 4 things. The first 2 over here, very, very simple. We've done this many times. F of 7, whatever's in the parentheses, is of course the input to the f function. So I go to the input column, I locate that particular input, and I can see that it is matched with an output of 6. Easy enough. Same thing for the second example. Look up 12 in the input column, and it of course is matched with an output of 3. Okay, now these next two are a little bit trickier. Now I'm being asked to find f inverse of 7. The problem is I don't have a table for the f inverse function. All I have is a table for the original function. So I'm going to have to think a bit creatively here. Okay? If 7 is an input in the inverse function, then it must be an output of the original function, because I already know that when you compare an original function and an inverse function, the inputs and outputs switch places. So if 7 is an input here, it must be an output in this table. In other words, this 7 is in fact this 7. The 7 in the output column of the original function. I can see that that 7 is matched with a value of 3, and so that would be my final answer. Take a look at this. In the original function, when you plug 3 in, you get 7 out. So of course, the inverse function is reversed. When you plug 7 in, you get 3 out. Now that you know how to do that, the second example is just the same. If 1 is an input to the inverse function, then it is in fact an output in the original function. So this 1 is this 1 right here, which of course is matched with a value of 10. In the original, 10 goes in, 1 goes out. In the inverse function, it's reversed. 1 goes in and 10 comes out. Now, one thing I could have done to make this a little easier on my brain is to simply have created a new table specifically for the inverse function. And that would help me work out these two examples probably in an easier way. How do I do that? If I have an original function table, how do I create the inverse function table? Well, it's pretty simple, because remember, all the inputs and outputs simply switch places. So all the numbers that used to be in the y column are now going to move over here into the x column, and vice versa. All the numbers that were in the x column here will move to the output column here. It is customary, I think, to write the x values in order from smallest to largest. So I am going to go ahead and rearrange the numbers here. It looks like the smallest value is 1, followed by 3, then 4, then 6, and then 7. I just grabbed those numbers from the previous output column. And now all I have to do is fill in the matches. 1 is matched with 10. Let's see, 3 went with 12. 4 went with 1. 6 with 7. And 7 with 3. This table now gives me the input and output values for the inverse function. And it's just completely reversed from the original function. Obviously, these two examples now become very, very easy if you use the inverse function table. Because, for example, to find f inverse of 7, I would just look up 7 in the inverse function table, and it's matched with 3. Similarly, to find 1 here, 1 is matched with 10. So when you're going through the homework, you can decide if you want to just think it through using the original table, or if you want to take a second and actually create a table for the inverse function. One last question, just to make sure you're following all of this. What if I asked you for this example to find me f inverse circle f of 10? We've learned that this is the same thing as f inverse of f of 10. Well, if you've been understanding the concept here, you should realize that you can just write down this answer doing absolutely no work. The answer has to be 10. Because if you start with 10 and you run it through the original function and get some answer, and then you take that and you put it into the inverse function just wipes out what the original function did. You'd just be left with what you started with. You can work out the math for this one and see it for yourself. F of 10, that would mean go to the original function, plug in 10, and we already know that 10 is matched with the value of 1, so f of 10 would be equal to 1, and then you're supposed to take 1 and stick it into the inverse function, well, here's the inverse function table. Here's 1 in the input slot, and of course it's matched with a value of 10. F inverse of 1 equals 10. Final answer then is 10. It's those two definitions you want to keep in your mind. The inverse function reverses the process of the original, and in the inverse function all the inputs and outputs have switched places.